All right, this week we don't have any activities, so I'm going to go through the slideshow for our two review days. Here's our first one. Looking at the first slide here, we've got the bell work with some graph review. So the first thing we're supposed to do is to graph it and then talk about the domain and range. So the graph, the first one, y equals 5 times 2 to the x, that's going to be exponential. I see the x's in the exponent. And it looks like it's exponential growth because my multiplier is a 2. My start at would be at 5. So I'm going to cross at 5, and it's going to be exponential growth. So something like that. Again, we're looking for the overall shape. Do we know what the shape is going to look like? For number 2, we've got y equals 5 times 0.2 to the x. So this is, again, exponential. But now the multiplier is between 0 and 1, so that's going to lead to a decay situation. So now this is exponential decay. Number 3, y equals natural log of x. So remember, natural log is going to be our base e. And if I were going to rewrite that, it would be e to the y equals x. So now the y is in the exponent. So this is going to be the inverse of an exponential, and it's the inverse of exponential growth. So this one is going to look like that. And there's our log graph. I'm going to focus on those three to start here. Domain and range, as we look at those, number 1, the domain, I've got graph going everywhere left and right. So my domain is going to be all real numbers. I think I've got that. And the range is going to be just the positive numbers. It's staying above the x-axis the entire time. So y has to be greater than 0. Exponential decay, that's going to be the exact same. So all reals. And y is going to be greater than 0. And we just talked about number 3 being the inverse of exponential growth. So that's where we switch the x and the y. So our domain and range are going to switch. So now the domain is x is greater than 0, and the range is going to be all real numbers. All right, number 4 and 5 is similar. They both have x now as the base, and our exponent on number 4 is 5/7. Our exponent on number 5 is 7/3. What to focus on there is the number, the exponent is greater than 1 or less than 1. Goes back to our earlier questions. So here I know that it's going to go through 0, 0, and I also know it's going to go through 1, 1, and this graph will as well. We also will not use any negative values for x because we have our fractional exponent, so I'm going to start there, and I have to go through that point. And the key here is if this number is less than 1, we know that it's going to be concave down, similar to the square root graph. So it should look something like that, as opposed to the y equals x to the 7/3, which would be concave up, which would look more like an x squared, that just right-hand side of it. Domain and range are going to be the same for these two. I have from 0 going to the right for the x's, and I have 0 going up for the y's. So that's x is greater than or equal to 0, and y is greater than or equal to 0, and then the same thing for number 5. So there would be some graphs that we might see. You may have to do some matching. We may move the graphs left, right, up, or down. We should know how to do that, dating all the way back to our transformations unit, adding things outside of the function, adding things inside of the function. Multiplying by a -1 would flip them over the x-axis. So some different things that we should always know. But those are kind of some of the main graphs that we've dealt with this particular chapter. Next slide here with the bell work is using some of our properties. So we'll look at the first one there. It says natural log of 1 over e to the 6th. So again, recall that our natural log is a base e. So if I were going to rewrite this, the question is what's the exponent? So it's e to the what is going to equal 1 over e to the 6th. So in this case, I need to take the reciprocal because the e to the 6 is in the denominator, and I need it to the 6th power. So remember what makes that happen. I have to have a -6. The next one, I've got 121 over 49 to the negative 3/2 power. So for that one, we're going to be looking at evaluating, and do we understand what all those things mean? So remembering with our exponent, the denominator is the root, the numerator is the power we're going to use, and then this negative is going to mean reciprocal, and it's the reciprocal of the base. So this is what I take the reciprocal of. I've seen students make mistakes with that, thinking it's something else. It is always the reciprocal of the base. That's why we flipped this e to be on the bottom, because it was a -6. All right, so as far as strategies here, I can really do any of those three things. I could take the reciprocal, I could cube all those numbers, or I could take the square root. I don't want to cube those large numbers, so I'm going to take the square root first. So when I take the square root, I get 11, and I get 7. And I just took care of this 2, so now my exponent is -3. And the next step that I would do is I would go ahead and take the reciprocal, so I get rid of the negative exponent, so that I'd have 7/11 to the third. And then I have to remember 7 to the third, and if I look at my exponent half sheet, 7 to the third, we're going to end up with 343. And then 11 to the third, I think, is 1,331. So there would be our answer for number 2. And the last one, number 3, we're going to be using some log properties. So our log property states that when I'm adding, change colors here, when I'm adding logs with the same base, I can put them together by multiplying the argument. So then I get log base 6 of 36. So I get 6 to the what equals 36. I get an answer of 2. So as I first look at this question, log base 6 of 9, and 6 to what power is 9? So that's some decimal, probably irrational. I have no idea what that is. Log base 6 of 4, 6 to some power is 4. And again, I have no idea what that is. But when we put those together, we end up, whatever those two decimals are, they're going to add up to 2. So that's actually what happens when we are able to use the log properties and get to a nice power of 6. 6 to the second is going to be 36. All right, so the next part would have been going over any homework questions. Again, you should stop into office hours and go over those, or after you submit your work. This is from the assignment from last week, but you can still go back, look at your submitted work, and see any hints, tips, what the correct answer is, how to get to that correct answer in the work by looking at the feedback after you submit your work. So remember, that's always there for you to kind of use the assignment to help as you go through. So again, I just have the assignment from last week clipped in, using some properties, being able to evaluate, very similar to what we did in the activity from last week. Being able to solve for x, that's a big thing that we're going to be able to do, where the x is in the exponent. The x can be the base. Here the x is the answer to a logarithm, which really means it's also the exponent. First step there would be rewriting. X is under a root. We should be able to solve for any x's, no matter where they are. Some highlighted things that we have talked about in past years, using our continuous change formula. The question is, how much time will it take to double on number 8? So here I want to know what the time is. Some students are confused because they don't know what the start is and what the end is. For this question, you can actually pick because it just needs to double. So if you start with 10, you want to have 20. If I start with 5, I want to have 10. If I start with 6, I want to have 12. So whatever I do there, because the first step is going to be divide by this number, so we're going to end up with a 2 over here. 2 equals e to the 0.0375 times t. Make sure we change that into a decimal. Some other ones, some graphing, different things. This one, again, being able to write an equation. The initial count was 5,000. It's doubling every 5 days. So times 2, not just to the D though. It's not doubling every day. It's doubling every 5 days. So it's D divided by 5. If it's been 10 days, it will have doubled twice, which would be 10 over 5, which would give us an exponent of 2. How many days have passed if there's 25,000 organisms? So now I want the L to equal 25,000, and then we're going to solve for D. So we're going to need to take the log of both sides at some point, not first, but at some point when that's up there. Half-life questions, talked about that. Another question here, find the value of R in the continuous change formula. If I know that the half-life is 1,800 years, so if I start with 100, I'm going to have 50 after 1,800 years. Here's our formula. So I want to have half as much over here, and this is telling me that the time is 1,800, and the question is, what is the R? So steps here, divide by 100, take the log of both sides. I would probably take the natural log of both sides because it's base E, bring down the 1,800 and the R in front, and then we should be able to solve. Again, those steps are all laid out in the worksheet answers after you submit it in Schoology. 15 was an extension one. You guys won't have to do anything like that. If really trying to put together some pretty large numbers, some log properties for that one. Answers. All right, so what have we looked at this unit? Properties of exponents. We should know our properties of exponents. We have the 3 of them listed there. Definition of logarithm, definitely need to know that. Forwards and backwards, be able to go from exponential to log, log to exponential. Our generic exponential equation, hopefully we're getting familiar enough with this. It should be at some point familiar as y equals mx plus b for linear. For exponential, there's our general exponential. Compound change formula, continuous change formula. We typically give you those formulas if you need them ever on a quiz or a test. And then as we looked at our properties from last week, I have log base b of x times y. I can separate it up into an addition. I could also go the other direction. These work in either direction based on what the directions are, based on what the simplifying is asking us. When I'm dividing the argument, I break it up into 2 logs that are being subtracted. And when I have an exponent, I can bring it down in front as a multiplier. Half-life questions. When half-life questions come up in some of the science courses, I know that they try to make it really nice where it's always like 10 and then 5 and then 2.5 and 1.25, where it always comes out being exact. Well, that's not real life. It's not always going to be exact. So we have to be able to set up an equation where we can find a half-life that's maybe not a whole number. So depending on what we're given, the situations, the first equation here would be if I knew what the half-life was, and I was asked either how much is left from an initial part after so many days, or so many years, or so many months, whatever this length of half-life is, x would have to be in the same units. But these a, x, and y could be unknowns. So this could be how much did it start with? If it has so many grams left after so many days. So depending on what you're given, one of those 3 things is probably going to be the variable as you're looking at being able to solve. I suppose the length of the half-life could also be a variable as well, but typically you'll be given that. And if you're given a continuous change formula, same idea, length of the half-life. This is like that setup that we had on the assignment. If I put in 100, this is going to be 50. And then you'll be asked to probably solve for the R value, or maybe you're given the R value and they want to know what the length of the half-life is. So you could be, again, given any of those as variables, but understand what half-life means, amount of time it takes for half of the initial amount to remain. This was an example that we did in class that was really based on, we wanted to be able to find log of all of these values, 0 or 1 through 10, when we were just given those 3. And using log properties to do that. So what we did is we are going to try to rewrite all of these values besides 2, 3, and 7 as using 2, 3, or 7 and being able to evaluate those. So as we start up here with log of 1, we know that that's going to be 0 because it's saying 10 to the what power is 1, and 10 to the 0 is going to be 1. Anything to the 0 is going to be 1. So that we can get there pretty quickly. But just to actually use one of our properties, I could write log 1. 1 I could rewrite as 7 over 7, or 2 over 2, or 3 over 3. I just picked 7 over 7. So 7 over 7 is the same as 1. So then I would use a log property. The property says if I'm dividing, I'm going to subtract and break it into two different logs. So log 7 minus log 7. So this decimal minus this decimal is actually going to equal 0. And we aren't surprised because that was the answer we got, just understanding the mechanics of a logarithm. All right, log 2 and log 3 we were given. So here's what we did for log 4. 4 we could rewrite as 2 to the second. Then we use a log property. We take the 2 and we bring it down in front as a multiplier. Use screen shade here to isolate that. So we bring the 2 down in front as a multiplier. So now it's 2 times log 2. They gave us that decimal. So 2 times 0.301. So log 4 must be that decimal. Log 5, I kind of have to come back to that one. So I'm going to go down to log 6. 6 I could rewrite as 2 times 3. So that I would break up log 2 plus log 3 equals that decimal plus that decimal that we were given up here. And so that must equal 0.7781. Log 7 they gave to us. Log 8. 8 I could rewrite. Well, I just found out log 4 is that decimal. So 4 times 2 would be 8. Break it up into two logarithms. Log 4, log 2, add them together, 0.903. I could have done 2 to the third, bring the 3 down in front, and it would be 3 times this number, and that's going to give me the exact same answer. So some different ways that you can do that one. 9, that one I did use exponents, log 3 squared. So the squared ends up going out in front as a multiplier. So 2 times log 3, 2 times that decimal from up above. So I get 0.9542. Log 10, 10 to the what is 10? We know that's going to be 1. And then I go back up to my log 5. Now I can do that one. I can rewrite 5 as 10 over 2. So log base 10 of 10 over 2. So separate that division into a subtraction of 2 logs. Log of 10 minus log of 2. Log of 10 is 1. Log of 2 is 0.301. And then I subtract those and I get 0.699. If I notice the decimals, they're slowly increasing up until I get to 1. So 0 to 1, and we see they're increasing, which makes sense. It's saying 10 to what power, and the value is getting bigger. Why are they all decimals? Because all these numbers are less than 10. So I need some type of root to make them 10 to some power to be less than 10. So that was one that we did just to kind of get used to using the properties to be able to evaluate if we're just given a few of those logarithm decimal approximations. All right, so a lot of solving being done. So what's our strategy going to be? So looking at different types of problems. Sometimes the problems are going to have logs on both sides of the equation. If I have logs on both sides of the equation, my first strategy is going to be to try to put those logs together. So use the properties of logarithms to put these together into a single log. So kind of going the other direction from what we did here. Once you get a log equals a log, as long as I have the same base, we end up with S equals T. So that's called the one-to-one property. That we're not dividing. I've heard that said before. We are not dividing. It's like sine or cosine or tangent. Log is like an operation. It is an operation. It means what's the exponent. So we just use what's called the one-to-one property. Is it similar to dividing? Yes, but that is not actually what's going on. So then we get S equals T and we solve from there, whatever those values or expressions might be. So logs on both sides, get single log equals single logs and drop out the logs. Number two, if we're given a single log. If I get to a single log equals something, the strategy there would be to rewrite it. So I would rewrite it as the base to some power equals the answer. And then depending on which of those is the actual variable, then we would solve accordingly. So if the variable is the b, then I would take this root. If the variable is this k, then I would just evaluate that expression. If the variable is the p, that's where I need to then take the log of both sides and go through that solving. And that's what number 3 is looking at. The variable's in the exponent. If I don't know the w, our strategy there is we're going to log both sides. We use log base 10 or log base e. I just use base 10. That allows us to then bring the w in front as a multiplier. So I get w times log h equals log c. And then I'm solving for w, so I just divide by log h. So my answer is w equals log c divided by log h. And again, using our scientific calculator, I know that that's going to work. Even if I think about there's a calculator on the phone, calculator on the phone is going to have log base 10, log base e. I don't think it has a change base. I don't think it has a base other than that. So we want to be able to solve these using log with base 10 or log with base e. All right, so that's the strategy when we're solving. Again, based on what the question looks like. Thinking about that one. All right, example, continuous change versus the compound formula, the compound change formula. So here's the situation. Julie invested $500 in an account earning 4.5% annual interest. Give the balance of the account after 5 years, assuming no additional deposits or withdrawals, if the interest was compounded annually or continuously. So if this is all the information, we don't know which of those it is. So if it doesn't say continuous, we're going to assume that it's annual, but here where it says we're supposed to do it both ways. So annual growth. So we give you the formula, so you have to know which one to use. So the annual growth, if it's not indicated as being continuous, we're going to use this top formula. So we'll be able to plug in the values. So 500 was the initial amount. R, 4.5% as a decimal, 0.045. N in this case is 1 annual growth. N is 1 up here, and the time is 5 years. So fill in each of those. You need to know what the variables represent. We'll give you the formula, but you need to know what numbers are going to go in where. If this said monthly, then N would be 12. And again, you have to make sure that you use parentheses appropriately. This whole thing would have to be in parentheses as you go through it. So make sure you can enter that correctly in your calculator and end up with $623.09. Then we're supposed to do it with continuous growth. Again, a little prediction. Should my answer be bigger than or smaller than this particular answer? It should end up being bigger than, because this is telling me I get my interest at the end of each year, and that's it. And then I get interest on that interest the following year for 5 years. This one, I'm continuously getting my interest, a little bit each day, a little bit each hour, a little bit each minute. So it should be a little bit more than that. So that one, we're going to use this formula, A equals P times E to the RT. Values are the same. Principal is 500. Rate is 0.045, and the time is going to be 5. I don't have an N. So again, make sure that you can enter that correctly in the calculator. You may need to put parentheses here around your exponent. Make sure that you can do that depending on how your calculator types it in. You might be able to get away with not, but you can still put them in there. So I would almost always put that in there to make sure that I get the order of operations. And we were right. It is a little bit more, very small amount, $3 more for the continuous. So that's an example of using our formulas. Here's an example from chemistry. Consider the formula pH equals 6.1 plus log of B over C, where the pH of a person's blood is the function of the person's bicarbonate concentration, B, and a person's carbonic acid concentration, C. A person's blood had a pH of 7.2 and her bicarbonate concentration was 24. What was the concentration of the carbonic acid in her blood? So I have these two values, the pH and the bicarbonate concentration. So those are the two things I can plug into my equation. So I did that already. 7.2 equals 6.1 plus log 24, that's the B, over C. And that's what I don't know is the C. All right, so now my job is to solve for C. So we'll go through those steps and be able to hopefully get C by itself and end up with some decimal or whatever this is going to end up being. So thinking back to our strategies, I have a single log that's written, so I want to get the log by itself. So my first step is going to be to subtract 6.1. So now I get 1.1 equals log 24 over C. So at that point, I have some options. I could use properties to rewrite it. If I do that, I'm going to end up with two logs. And I don't want to make it more complicated. So what I would do at this point, I know when it just says log, if it just says log, I know that the base is going to be 10. So here I've got a base of 10. So at this point, I have the single log. So I should be able to just go ahead and rewrite. So the base is 10. The exponent is 1.1. And the answer is 24 over C. So from here, I can go ahead and now solve for C. So C is in the bottom of the fraction. So my first thing I'm going to do is I'm going to multiply by C to get that out of there. So now I have C times 10 to the 1.1 equals 24. And now I want to solve for C, so I'm going to divide by 10 to the 1.1. And now I have C equals, then I pick up the calculator, 24 divided by 10 to the 1.1, and I end up with 1.906. I am not a chemistry teacher, so I do not know what the units on that are. I've heard people talk about moles in class previously, so that maybe that's what it is, 1.906 moles. But whatever that is, that's what our C value is. That's the concentration, 1.906. All right, the next thing here is being able to find inverse functions. So inverse functions, we're going to do some rewriting and some solving. So I start off with a log equation. So I've got g of x equals log base 8 of x minus 3. So to find the inverse, remember we switch the x and the y, and then we solve for y. So here I have a single log, and I'm going to rewrite it. I'm trying to solve for y. So as I rewrite it, just like we did before, base is 8, exponent is x, and the answer is y minus 3. So I get 8 to the x equals y minus 3. I'm trying to solve for y, so I add 3 to both sides. So I get 8 to the x plus 3. So we should be able to rewrite these now in exponent form. We want to solve for y, and I want to use my appropriate inverse function notation. So there's number one, just switch the x and the y, and then solve for y. Number two, there's our answer for number 2. Switch the x and the y again, and I have x equals y to the 3/4 plus 4. So now I want to get the y by itself. I see this exponent. Sometimes students get all excited. They know what to do. It's to the 3/4. They're going to take it to the 4/3. But first, you have to get rid of this plus 4. So subtract 4 first. So I get x minus 4 equals y to the 3/4. Then I can take it to the 4/3 power, take this side to the 4/3 power. Remember how that works, power to a power, we're multiplying. I get y to the 12 over 12, which is y to the 1. So the inverse of h of x is x minus 4 to the 4/3, and we can leave it just like that. And the next one, a little bit more steps here, x equals 3 to the y minus 5 as we switch. And now I need to solve for y. So the y is in the exponent. Variables in the exponent I'm trying to solve for, I'm going to log both sides. So that's what I did here. You see it's already crossed out because I did the solving, but log of 3 to the y minus 5. I take the y minus 5, I bring it down in front as a multiplier, so that's no longer up there. I want it as a multiplier because I know how to undo multiplication. I divide. So now I divide both sides by log 3. I log this side as well to keep it as a balanced move on that first step, so I have log x, and then I divided by log 3. So all that would remain over here would be y minus 5. How do I get rid of the y minus 5? How do I get rid of the minus 5? I'm going to add 5. So I add 5. I can add it out over here. So 5 plus log x over log 3. Or I could write it as log x over log 3 plus 5. This I could actually rewrite as well. Log x divided by log 3 is actually the same thing as log base 3 of x. I'm just going to keep it probably like this because I know that there's a log base 10 button on the calculator. So that will allow me to be able to solve or evaluate if I'm asked to do something afterwards. All right, so that's what we did kind of in class to get going as a start of our review day. Then we talked about what was going to be on the Chapter 9 quest, and we'll see those different items as we go through. You can pause that and read through that as well.